Alright, coming to the next example. The line graph LG of a simple graph G is defined as follows. So we have a simple graph G, and then there is something called the line graph LG of that simple graph, and that's how we define this line graph LG by these 2 points. The first point is there is exactly one vertex VE in LG for each edge E in G. So this means that for every edge E in G, there will be a corresponding vertex VE in LG. Okay. What is the second point? For any two edges E and E prime in G, so there are two edges E and E prime in G, LG has an edge between VE and VE prime if and only if E and E prime are incident with the same vertex in G. Okay, this looks a little bit abstract right now because we have not really looked into the examples. We will go through the examples and it will be more clear. Alright, so as of now you know that there is something called the line graph LG of some graph G, which is defined using these 2 points, and then you have to answer these questions. You have to answer which of the following statement is true. You are given statements P, Q, R and S, and you have to determine which of them is true. Okay, so as of now you know that there is something called line graph, or if I give you a graph G, then what you can do is you can create the line graph for that graph G. Okay, so let's look at the statement P. The statement P is the line graph of a cycle is a cycle. What does this mean? I give you a cycle and I ask you to find the or create the line graph of that cycle. And the statement P says that that line graph of that cycle is also a cycle. So let's try to see what happens when we create the line graph of this graph G, which is a cycle of 4 vertices. Alright, this is a cycle. Okay, so how do we get the line graph? Using these 2 points, because that's how we have defined the line graph. So there is exactly one vertex VE in LG for each edge E in G. So how many edges are there in G? 4. So for each edge there will be a vertex in LG. So suppose this is an edge AB. So there is a vertex VAB corresponding to this edge in the line graph. Similarly, there will be a vertex corresponding to this edge, there will be a vertex corresponding to this edge, and there will be a vertex corresponding to this edge. There will be 4 vertices in the line graph LG. That is the first point. And if you actually draw the line graph LG, it looks like this. So this is a vertex VAB. This vertex VAB is nothing but the vertex that corresponds to this edge AB. This vertex VBC corresponds to this edge BC. This vertex VCD corresponds to this edge CD. This vertex VDA corresponds to this edge TA. Next, this is the first point. The first point gives you the vertices of the line graph. So far we only have these vertices. The second point is about how we get these edges in the line graph. Alright, first point is about the vertices, how you get the vertices of the line graph from the original graph. The second point is how you get the edges of the line graph from the original graph. So what it says, see, it was very abstract in the beginning, but now if you will look at this example, it will become more clear to you. For any two edges E and E prime in G, for any two edges E and E prime in G, LG has an edge between VE and VE prime if and only if E and E prime are incident with the same vertex in G. So what does this thing means? E and E prime are incident with the same vertex in G. So let's understand this with an example. Suppose AB and BC. AB and BC are two edges. Their corresponding vertices in LG are VAB and VBC. And if we say are AB and BC incident with the same vertex in G? That means that do they have a common vertex in G? Yes, they do have. AB and BC, they are connected at this vertex B, or they have this common vertex B. So that's why it says if and only if. So you have this edge AB, you have this edge BC, they have this common edge B, so their corresponding vertices VAB and VBC will have an edge because they have this common vertex. You can do this for all the edges. Similarly, VBC and VCD will have this edge because C is common to CD and BC. Alright. Similarly, VCD and VDA will have this common edge because D is a common vertex of edge DA and CD, and similarly you will get this edge. Okay, so we started with a graph G and we obtained the line graph of that graph G. So this LG is the line graph of this cycle. Is it a cycle? Yes, it is a cycle. So we know that line graph of this cycle is a cycle, but can we, this is a special case, can we say that line graph of any cycle is a cycle? Well, let's think about it a little bit. Suppose you had a cycle, suppose you had a bigger cycle than this. What would you have? You will have more vertices and more edges, but it would look like this only. The structure would be like this. There will be more edges and more vertices. So if you take any two adjacent edges, they will be like this, and you will have a corresponding vertex for this edge like this, and you will have a corresponding vertex for this edge like this, and then there will be an edge between them because of this common vertex. So you can do it for bigger cycles, and what you will find that you will always get cycles. In fact, the line graph of a cycle is isomorphic to that graph, right? This was a cycle of 4 vertices, and when you drew the line graph was also a cycle of 4 vertices. This is isomorphic to this, and you do it for any cycle. You take the cycle of 6 vertices, you will get the line graph of which will be a cycle of 6 vertices. It's quite obvious if you take the definition of line graph, because that's the way we draw them. All right. So yes, we know that the line graph of a cycle is a cycle. That's why the statement P is true. What about the statement Q? The line graph of a clique is a clique. What is a clique? Clique here means the complete graph. What is the complete graph? Complete graph is a graph in which every vertex is connected with every other vertex. So let's take statement Q and try to see what do we get if we take the line graph of a clique. Okay, this is a clique, right? Because every vertex in this case is connected with every other vertex. This is an example of a clique, and then we'll see what will be the line graph of this clique. How many vertices will there be in the line graph? The number of vertices in the line graph will be equal to the number of edges in this graph. This graph has 6 edges. You can see that easily. 4 are these and 2 are these. So there will be 6 vertices corresponding to these 6 edges, like VAB corresponds to this edge, VBC corresponds to this edge, and so on. VAC, VBD, VCD, VAD. And VAB and VBC have this common edge. VAB and VBC have this edge because the edge AB and the edge BC out here share this vertex. Similarly, VAB and VAC, they have this edge because out here edge AB and edge AC share this common vertex A. So you can go ahead and try to draw the complete line graph. Try to draw the line graph for this clique, and you will get something like this. Is this a clique? No, this is not a complete graph. You can see that this edge is missing, this edge is missing. This is not a complete graph, and this is not a clique. So Is this statement true? No, it is not true, because we have given a counter example where we started with a clique and we ended with the line graph that was not a clique. So we can say that statement Q is false, because if we want to prove something false, a single counter example is enough to show that that statement is false. Okay, that was statement Q. We know that statement Q is false. Coming to the next statement, line graph of a planar graph is planar. I suppose everyone understands what is a planar graph from your theory classes. Planar graph is something which you can draw in a plane without having the edges crossing. Okay, and if you remember this property of planar graphs, if a graph is planar, it implies that number of edges is less than or equal to 3 times the number of vertices minus 6. This is a very useful property of a planar graph, that it has to have the edges less than or equal to 3 times the vertices minus 6. And from here what you get is, if you negate this thing, you get, suppose E is greater than 3v minus 6. This would imply that the graph is not planar. This statement is just the contrapositive of this statement. Planar implies E is less than or equal to 3v minus 6, but if E is greater than 3v minus 6, it would imply that the graph is not planar. Alright. Okay, so we take this planar graph and try to find the line graph. Okay, you can ask, why did I choose this planar graph? The answer is, I spent 2 hours to find a planar graph whose line graph will not be planar. See, for smaller planar graphs, if you take small planar graphs, right, and you look at the line graph, it often comes planar. So I had to spend some time coming up with this sort of planar graph to show it to you that the line graph of this planar graph is not planar. Okay, so yeah, so I mean, it took me some time to come up with this graph. It's not like obvious that you will come up with this thing in the first time. Alright, so what can we say about the line graph of this planar graph? Okay, in the previous two cases, what we did, we started with a graph and we actually drew the line graphs. Okay, in this case we are not going to do that, because the line graph of this graph would be hideous. It would be ugly. It would be tedious to draw that line graph. It will take a lot of time, and if we can do it in a more analytical manner, that would be very helpful, because we know these properties about planar graphs. So these properties are about, they relate the edges and the number of edges and the number of vertices in a planar graph. Okay, what if we suppose we drew the planar graph of this graph, suppose we drew the line graph of this graph, what would be the number of vertices in the line graph? That would be equal to the number of edges in this graph. So how many edges are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we know that number of vertices in LG is V, and then we'll see what will be 3v minus 6, because then we need this value 3v minus 6 to use this property. So 3v minus 6 will be 3 times 11 minus 6, which is 27. Alright. What about the number of edges in LG? See, we are not drawing LG. We are trying to find these number of vertices and number of edges using our rationality, using our mental capability to do some sort of analysis. Okay. So the number of edges in LG, how can we find them? What do we know about the edges in LG? See, if you remember the point 2 from the definition of line graphs, you know that there is an edge between two vertices in LG if their corresponding edges have a common vertex in the original graph G. So the vertex corresponding to AB and the vertex corresponding to BC will have a common edge. They will have an edge between them. The vertex corresponding to edge AB, the vertex corresponding to edge BC will have a common edge because they share this vertex B. So let's try to find the number of edges. Let's start with the vertex corresponding to edge AB. This shares this vertex with this. This shares vertex B with edge BC and vertex A with AC, AD, AE, AF and G. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. So the vertex corresponding to this edge AB will have a degree 6, or it will have edges, it will have 6 edges going to other vertices, right? Just think about the second property. There will be a vertex corresponding to this edge AB, which will be VAB, and then there will be an edge going to VBC, there will be an edge going to VAC, an edge going to VAD, an edge going to VAE, an edge going to VAF, an edge going to VAG, 6 edges. Alright, so 6. Then let's talk about AC. Now when we talk about AC, we know that this will have an edge, VAC will have an edge going to VAB because this is common between this and this, but this we have already counted, so we will ignore this. So from here we know that the number of edges can be counted like this by finding the edges that share vertex with this edge AC in this graph. So that will be 1, 2, 3, 4, 5, 6. Why? This and this share vertex out here with this, and this and this share the vertex A. So this is 1, 2, 3, 4, 5, 6, again 6. What about AD? We know that D is shared by CD and DE, so 1, 2, and A is shared by these 3, so 1, 2, 3, 4, 5. What about AE? 1, 2, 3, 4. Okay. What about AF? It's 1, 2, and 3. What about AG? It's just 1. Alright. See, we don't count the edges going to these, the vertices corresponding to these edges, because we have already counted them. That's why we have marked them using these stars. What about AC? Just 1. What about CD? Just 1. What about DE? Just 1. What about EF? Just 1. What about GF? Right, 0, because when you will look at this, you will find that every edge that will come out of the vertex corresponding to GF has already been counted, because all these are starred. This will come out to be 29. So what do you know from this? 3b minus 6 was 27 and E is 29. So E is greater than 3b minus 6, and thus you can conclude that LG is not planar. So we can say that statement R is false. Coming to the last statement, which is the line graph of a tree is a tree. So let's take a tree. This is a tree. How a tree is defined? A tree is a graph that doesn't have a cycle. That's how a tree is defined. This is a very simple example. If you take the line graph of this tree, you will get something like this. So there will be a vertex VAO corresponding to AO, a vertex VBO corresponding to BO, a vertex VCO corresponding to CO. And if you try to find the edges, so VAO, this will have an edge for B with BO and CO. BO will have an edge with AO and CO. CO will have an edge with BO and AO. And this is a cycle. This is definitely not a tree, because a tree is a graph that cannot have a cycle. Trees don't have cycles. So this statement S is false too, because the graph was tree, but the line graph is not a tree. So P was true, Q, R, S were false. So only P is true, so option A. Alright. Okay, next example is very simple. Let G be a complete undirected graph on 6 vertices. If vertices of G are labeled, then the number of distinct cycles on length 4 in G is equal to, then we have these options. What do we have? We have a complete undirected graph on 6 vertices. So we have this graph. This is a graph of 6 vertices. and it's complete. Every vertex is connected with every other vertex, and then you give it some sort of labeling, and then you find the distinct cycles of length 4. So this is a cycle of length 4. I've shown it highlighted out here. So how do I find a cycle of length 4? Out of these 6 vertices, I choose 4 vertices, and that will be a distinct cycle. So out of these 6 vertices, I can choose 4 vertices in 6cc4 ways, which is 15 ways, right? I can select 4 objects out of 6 objects in 64, which is equal to 15 ways. Thus there will be 15 distinct cycles, and option A. Alright.